warming up. So what are we in here in for? We are in for an introduction today. A little bit more practical information. Welcome to the course. Giving some introductional examples, and you can say a very, very brief outline of the course. As mentioned, you can see the reading plan. Oh, sorry, the question.
It's just before we started, you have written that the 24th of October, which is a Tuesday and not a Thursday, and all the other assignments are on Thursday.
Yes, I remember there was a reason for doing that on a Tuesday, but I did do it. The reason for doing that is that this year, this autumn break doesn't fall at the same point in the semester as most years, because the semester is starting a little bit later. So all the weeks are shifted 1 week. So traditionally, I would have the hand-in of that before the autumn break. But that will be too short time. And I can't push it to be before, given the time we are at right now, and given that I actually want to cover what you need to use before handing in the assignment. I hope you appreciate that. And then I put it on a Tuesday, because the next one opens soon thereafter, and also to allow the time for peer grading. So it's to buy a couple of days for peer grading.
It's just because I noticed the difference, so I just want to ensure that.
Yeah. It was on purpose. It was related to peer grading. Now I can rewind my memory to a couple of weeks back. And then after the introduction, we'll get on to, you can say, the more scientific content, starting with multivariate random variables, which is something that some of you know of, but I think also some of you do not. I'll get back to details about that. And for those of you who know, take it as a recap. So these are where to find me. As I said, I'm usually sitting just a few meters beyond that wall. Now, at 10 o'clock, Jesper and Sebastian will show up as TAs. I also plan to be here. There's 1 week where I cannot be here, neither for the lecture, but I have thought about how to do that. So I will of course be here Friday mornings, but if you have, you can say, other questions, feel free to find me one way or the other. Right now, an email is probably the easiest way to get me. So, what is actually the intention with this course? What should you be able to do? So, these are some data. And what is it that we see? We have muskrat skins and mink skins that are traded in Canada. It's a fairly old data set, about 100 years old. And why do I show this? Well, if you look at this data, what do you see? What would be the reason for looking at this data? What would you want to do? I would like to say, well, that's all fine. How can I describe this? And my purpose for that. Now, if you are into, say, finance, whatever, what you want to do is to know a little bit about tomorrow, at least a little bit more than everyone else. And if you do that, then you have a competitive advantage. Likewise here, if you know what's going to happen in the future, that's the purpose of this course. I mean, that's one of the main purposes. But in order to figure out how do I describe the future, you have to say, well, what can I use of information from the past? So what do we see here? We should see two different time series, one for muskrats and one for mink. The numbers for mink are just way smaller than muskrats. For muskrats, how would you describe what you see there? We will get into details how to do this later on, but I think it's good to just mentally say, what is that actually we're looking at? What do you see there?
High variation and over
Yeah, increase.
So increase in overall?
Yes. So we have an overall increase and we have a large variation. I would add one thing only to that, and that is the variation is also increasing. So that means the larger the values are, the larger the variation is. Have you seen that before in other cases? In other statistics courses? I guess some of you have. Maybe not so many. So the purpose is to make a forecast. Could be what is added here. Now, what is the likelihood that we're going to observe values along those two lines?
0.
0, exactly. Why?
Well, because so the probability of observing something continuous is 0, right?
If we assume a normal distribution, the probability of observing a particular number is 0. Now, in a particular case, it's actually the number of skins that are traded. So that's not going to be a decimal number. So we have integers. In practice, in all cases, you have rounding. So even though in theory the probability is 0, in practice it will be greater than 0. However, for practical reasons, in this case, we're looking into the somewhere between half and a full million of skins. I mean, a particular value, we're not going to hit that. So what we want to say, we want to have a prediction interval. We're so, say, 95% confident that the number of muskrat skins will be in this range. Likewise, the mint skins will be in that range. Then we can say something with a larger probability something is going to happen. It doesn't mean that things will not fall outside. To take an example, these are from financeyahoo.com just because they allow showing data publicly afterwards from their website. If you look, the blue line here is the value of coloplast looking over a time window of 1 month. So if you look at this, what I see at least is, well, you have some oscillation, and you can say it ends lower than it started. So maybe this is not the best time to buy. Now, if you instead of looking at it for 1 month, look at it for 1 year, you do not see the downward trend anymore. What do you see? How would you describe this if you just look at the blue part? Yes?
It's like some steps. Some steps with some noise on it.
Yeah, so it jumps between some discrete steps at some random point. It just has some jumps. So you have some events, and then you have, you can say, some periods where you just fluctuate, have some noise parts. Exactly. But overall, the level is pretty much stationary. You can say, if you look at the whole process. Now, if you look at all the data that is in there, the story is different. There is a marked increase over time. So that's good for someone who bought something early. Maybe for the last year, it's been a little bit more of a stationary process. So this is just to say, whenever you have a process, some process you can look at that on different timescales. And your conclusion depends on how you actually sample things. I'll come with other examples later on where you say, well, you have a daily cycle in something, but if you just look at the daily mean values, well, you ignore that. So a lot of times where you have potentially more information, but you may not need it. So there's a lot of choices to make regarding how you sample and what is your, you can say, the period that you look at. And how to pick that. Of course, we'll talk more about that later. But basically, you should say, well, are you into a long-term investment in this case, or are you looking at day-to-day or intraday trades? You wouldn't use a model for that for intraday trades. Then you would go back, actually not even to this, then you would look at intraday values. So it depends on your time horizon for what you're doing. How far ahead are you going to make predictions? You should not just use what is available, you should consider how to use it. But we'll get back to some of those things in various contexts. And now if we took the log of all the values instead of just showing the actual values, now it's almost nice. From a statistical point of view, it looks almost like a straight line, right? So you have, in the log domain, you have a linear increase. I don't know if you can figure out what that means. Anyone? I heard someone mentioning introduction to finance earlier this morning, so I don't know if you can say, what does that actually mean? Yes?
They have an exponential increase.
So they have an exponential increase, so that means they have a growth per day that is fixed in percent, not in points. Another slightly older case, but we should also keep in mind that we can only predict some things. These are the monthly airline passengers in the US some years ago, and what you can see here is that there's a clear annual pattern. So if you were at some point in the middle of 2001 and were to make a prediction, you would probably predict something that was sitting up here with a fairly small uncertainty because the annual pattern is fairly stable. But then something happened. I don't know, some of you can probably remember. 9/11, exactly. And if I actually continue the data here, it wouldn't be that many years until it was back on the same increasing trend and the same seasonality. But there are events that just changes everything. We can detect those as well. Of course, not before they happen, but after they happened. We say, what is the likelihood of having a change? That's something we'll touch somewhat upon. But the focus in this course is on, you can say, continuous distributions, mainly normal distribution, or we'll make transformations so we can assume that it's normally distributed for time series. And we will try to make predictions, you can say, given, assuming everything else is equal. Sometimes we can add parameters that we can describe for other things. One case for that is the following. District heating, VEX is one of the larger networks in Copenhagen. It's actually the transmission network, and then there's distribution networks around it. So it connects pretty much all district heating networks in the greater Copenhagen area, actually reaching all the way to Roskilde. So it's more than 1 million people getting heat from here, and a lot of companies as well. So if we look at the heat consumption over a winter here, well, again you see a lot of oscillations. Then if we look at, well, what is driving that, you can say the overall, there's a movement, and then there's a fast oscillation in between. I don't know, can you figure out what is happening? Yes? So it's a day-night cycle, exactly. We'll get back and get closer into that in a moment. Then we have the air temperature, the ambient air temperature here. So you can see when it's cold, the consumption goes up. No big surprise. But if we do not have that information, then it will be difficult to explain what happens over here. So we have a daily cycle, and then we have a temperature-dependent cycle. If we just did ordinary linear regression, just plot the air temperature and the heat consumption, it looks like this. Based on an introduction to statistics course, and you saw this, would you be happy? Why? I see someone shaking their heads. I would not fail any students if they just had that course looking at this and say, yes?
First of all, the variation is not uniform.
No, true, the variation is a little bit higher when it's colder than when it's warmer. But it's very difficult to see that here because we just picked a period of time, so we don't have much data when it's warm. So when you just look at it, it's difficult to see because the variation is also down here is also very small. Whereas in the middle, where you have a lot of data, the variation appears larger. But is that due to more samples, or is it because the variation is larger? It's an observation that needs to be addressed. Definitely so. Other comments? I think there's one fair comment that you can definitely say based on this. And that is, if you look at the line here, then it seems that there's fewer residuals above than below when the temperature is high. And likewise down here, it seems that you have an overrepresentation of positive residuals up here than negative. So the linear assumption is maybe not perfect. I think that's the only thing you could say from here. But now, this is not an introduction to statistics course. So, what is a dynamical system? And why do I ask about that right now? It's related to your comment on day and night. Yes?
Well, it's a state that evolves over time. Is over time.
It is a state, it's related to states that evolve somehow over time. Typically you will describe with some difference or differential equation. So how does that connect to district heating? Yes?
Because like the air temperature and the district,
There is a dynamical system there. You can say the coupling is the state. And the state is not necessarily the consumption right now. The state is the temperature of, say, building mass. So whenever the buildings are warm, the consumption is small. When the buildings are cold, the consumption will increase because of thermostats. But I don't know how many of you have been coming home to a cold house because something was broken, and you fixed it and the temperature got up again. How many have tried that? Or tried that the heating was broken and actually it was okay for a while?
Oh, actually also might happen. You turn it down when you go out to safe, then you come in, it's cold, and you turn it over too much.
True. Could you everyone hear that? You could, to save energy, you would turn down the thermostat when you're leaving the house, and then you'll turn it up again when you get back home. Now, depending on your heating source, it may actually take hours before it reheats. So you will kind of overshoot where you want it to be. And you should actually turn it down way before you leave home, because it's still going to be warm. So that's some of the things that happens. So if we look at the residuals, as in the errors, over time, you can see the daily pattern throughout. If things were nice and independent, that is the assumption when you do just a linear regression model. You assume that there's no dependence. It should look like this. This is what we call white noise. I don't know if you know where that term comes from. Anyone?
It's from audio.
Sorry?
It's from audio things.
Yes, it's the same expression used in audio settings, true? But it actually comes from the light. Because if you have white light, it means that all frequencies are represented. And that's the same thing you do for audio signals. You have all frequencies are equally represented. then there's no information about particular colors. So that's why in audio settings you can say a different colored noise, say pink noise, we have extra high frequencies. In this case, you have some very warm noise because the frequency that's in there is the daily cycle. So it's a fairly small or low frequency signal. So that was kind of a motivation for what we're going to be doing things. In the last example here, what we'll do is, of course, to describe this. What makes it different from the airline case is that here we actually have two different variables involved. And I will say how to go to n not being too large, but it's also where calculation time is just increasing, and estimation time even more so. So we'll try to use examples that we can do without spending too much time waiting. On the other hand, I also like to get to some things that are real-life cases, and that's a balance, and there's no nice solution. So sometimes you will have to wait a little bit of time, or I will give you hints to say, in the interest of time, you can do this when playing around. Okay, so today we will start looking at multivariate random variables, not just 1- and 2-dimensional, but that we have to use n-dimensional. And then, as kind of indicated, what we want to do is doing predictions. We'll first base it on the general linear model and different alternative ways of using it. So, how many of you have made general linear models using matrix notation? Some, but not so many. That's expected. We'll of course go to more time series models where that's actually the purpose of things, because that's the purpose of the course. And that involves some theory on linear systems, and we will do things with external inputs and multivariate systems as well. Mostly bivariate, but everything we do there can be expanded to any dimension. So basically, what is that we want to achieve? We want to be able to characterize time series. Are there seasonal components? Is there a trend? How is the variation? That goes for different signals. One of the elements in characterizing that is so-called correlation functions. That is saying, how much does this signal depend on the past? Covariance functions, similar to correlation functions. We're going to talk about stationarity and linearity. We're going to focus on things that are stationary and linear, or can be made stationary and linear, because not everything is, but many things can be transformed and assumed to be. And then, in the signal processing, often used things are filtering, where we'll touch upon some methods. There are tons of methods out there. We won't cover everything. Modeling, how do we describe systems? And then predictions with uncertainty. And I want to underline that, since the likelihood of observing a particular number is 0, unless you specify some measure of uncertainty, you provide next to no information. Because if you don't say anything about, I expect to observe 99.74, well, but what is the interval where you care about? Do you actually provide any information? Could it be minus 1,000 and minus 2,000 are equally likely and still likely? You have not that much information, but if you say the interval has a width, have 95% confident that it's within 1 unit, then you have a lot of information. So be sure to always communicate uncertainty. I can say that for grading, that's one of the things that if you don't do that, I'm mean. I don't like to be mean, but that's one of the things where, because just coming with a point estimate in a statistics course doesn't provide much value. There will be a few places where I say it's okay to do that, but it should be declared that it's okay to just give you that. At least when it's related to data. So when you have data that you're trying to estimate things from, you need to add the uncertainty. So today, as promised, I will talk about multivariate random variables. But I think also now is the best time to have a break. So let's just do a 10-minute break and start 10 minutes 2.